Hi, my name's Paul VanKoughnett, and today I'd like to talk to you about some of my research in stable homotopy theory and its relations to algebraic geometry. My research is in the area called chromatic homotopy theory, which began as a way to study periodicity in the stable homotopy groups of spheres. So this is a picture of the stable homotopy groups of spheres at the prime 5. Each of these dots represents a z mod 5. And we can see at least 3 different sorts of periodic patterns in this diagram. So there's a simple pattern with a short periodicity at the bottom, there's a pattern with a longer periodicity on top, and there's a pattern with an even longer periodicity in the middle. So the idea is that we can think of these as sort of different wavelengths that are superposed with each other to make up the entire pattern of the stable homotopy groups. And each of these different wavelengths can be probed by using different kinds of cohomology. So the idea behind chromatic homotopy theory is that there is a filtration on the entire stable homotopy category called the height filtration, and height n cohomology theories reveal certain periodic patterns inside stable homotopy groups. At height 1, we have things that are accessible through real and complex K-theory. At height 2, these patterns can be accessed by topological modular forms and other designer cohomology theories that have been made to study these patterns. And in general, at height n, there are certain theories that have been constructed to isolate height n phenomena. Let me say a little bit more about how this works. Let's fix a prime P, and everything that I talk about will be completed at P. Any P-complete spectrum X has a filtration like this in terms of what are called its Ln localizations. So the 0th localization is the rational homotopy type of X. The height 1 localization of X also includes some height 1 information about X, and so on and so on. We can study these using this suite of theorems, which were mostly developed by Hopkins and Ravenel. First of all, if X is finite, if it's the P-completion of a finite complex, then it's the homotopy limit of this diagram. Second, there's a pullback square expressing each ln x in terms of ln minus 1x and another object called the kn localization of x. So we can think of these kn localizations as sort of the associated gradient of the height filtration. And then finally, there's a spectral sequence which computes the kn local homotopy groups of x, whose input is the cohomology of the nth Morava stabilizer group, which is a profinite group, acting continuously on the nth Morava E theory of X, which is a certain homology theory of X. So the first thing I'd like to talk to you about is work related to topological modular forms. So this is what I called a designer spectrum, or designer homology theory. It was constructed using techniques from derived algebraic geometry out of the moduli of elliptic curves. And it's been used to study stable homotopy theory at heights 1 and 2. Now, given any homology theory like this, one important fact about it we can consider is its ring of cooperations. And ideally, we can use this to figure out the associated atom spectral sequence. So the ring of TMF cooperations and the TMF-based atom spectral sequence were first studied by Behrens, Ormsby, Stapleton, and Stoyanovska, who computed TMF star TMF rationally and K2 locally. In joint work with Dominic Culver, we continue this story by computing the ring of K1 local TMF cooperations. So we show that this can be identified with a purely algebrogeometric object, the ring of ordinary 2-variable p-adic modular forms, and that it has a simple algebraic description in terms of its theta algebra structure, which is a natural structure that exists on the K1 local homotopy of any highly commutative ring spectrum. We also compute the associated atom spectral sequence and show that this agrees with a simpler object, namely the K1 local atom spectral sequence based on real K-theory. So now I'd like to talk about Goerss-Hopkins obstruction theory. This is a machinery for, given a homology theory E, trying to lift E homology data to homotopical data. So if you have an E star E comodule, which is the sort of algebraic data that looks like it could be the E homology of a spectrum, is it actually the e-homology of a spectrum? And if so, how many such spectra? More interestingly, if we have a comodule with extra structure, like a commutative ring structure, can we lift it to a spectrum with a highly commutative ring structure? So the main application of this obstruction theory is the Goerss-Hopkins-Miller theorem, which states that there's an essentially unique highly commutative ring structure on Morava E theory. In joint work with Piotr Pstrągowski, we generalize this considerably. We prove that there is a Goerss-Hopkins obstruction theory associated to any nice infinity category equipped with a suitable periodicity operator. The classical examples, the obstruction theories for spectra, can be recovered from periodicity on the infinity category of synthetic spectra, which is a category that interpolates between the category of comodules and the category of actual spectra. In doing this, we uncovered some delicate and unnoticed convergence issues in Goerss-Hopkins obstruction theory. We're able to resolve these issues in certain cases, notably Morava E theory, ordinary homology, and Brown-Peterson homology. And we show that these convergence issues are related to the existence of vanishing lines in atom spectral sequences. So we think that there's a lot of interesting work still to be done here about this question. In my thesis, I did some other work related to obstruction theory. So the input to obstruction theories for constructing highly commutative ring structures is the algebraic data of power operations. And I described power operations on LKn-1 En, which is a sort of transchromatic object that interpolates between height n-1 and height n. As an application, I proved that there are infinitely many highly commutative ring structures on LK1E2. So this is very different to the case of Morava E theory itself. This object has a bunch of exotic commutative ring structures which don't come from the canonical one on E2. Now I'd like to talk about some work in progress, which is related to duality resolutions for the K2 local sphere. The starting point here is this theorem of Behrens, which says that at the prime 3, there is a K2 local fiber sequence splitting the K2 local sphere into a spectrum called Q2 and its Spanier-Whitehead dual. Q2 can be defined purely in terms of algebrogeometric information. So it's the limit of a small diagram involving topological modular forms and topological modular forms with level 2 structure, and the maps in this diagram have to do with natural operations on elliptic curves with level structure, such as quotienting by the level structure. In joint work with Behrens, Irina Bobkova, and Dominik Kulver, we're proving that at any prime greater than 3, and for any level L, which topologically generates ZP cross, there is a K2 local fiber sequence of the same form. So the K2 local sphere can be understood in terms of elliptic curves with level L structure. Here QL is defined analogously to Q2. Now, Behrens' decomposition of the sphere is an interpretation of an earlier decomposition by Goerss, Henmehold, and Resk. So they wrote down a resolution of the K2 local sphere at the prime 3 in terms of homotopy fixed points of height 2 Morava E theory with respect to certain finite subgroups of G2. And you can see that this resolution has a certain kind of self-duality which is visible, and that's the reason that Behrens' resolution involves this decomposition into two dual halves. As a stepping stone to prove this, they constructed an algebraic resolution of the trivial module over the group G2. So this is not a projective resolution, but it's a finite length resolution in terms of modules which are induced from finite subgroups of G2. So in joint work with Eva Belmont and Catherine Ray, we've constructed an analogous resolution of the trivial module over the general linear group GL2Z3. And we've been using this to compute continuous group cohomology of this group. So this is an application of techniques developed in stable homotopy theory to purely algebraic questions. And here are some papers online about this. So thank you for your time.